In 1950, the physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory and asked a question that has not been answered since. Where is everybody? The universe is 13.8 billion years old. It contains an estimated 2 trillion galaxies. Our galaxy alone holds between 100 and 400 billion stars. A significant fraction of those stars have planets. A significant fraction of those planets exist in zones where liquid water is possible. The numbers suggest that life, if it emerges with any regularity at all, should be everywhere. The galaxy should be loud with it. Signals, structures, evidence of engineering on astronomical scales. Something. Instead, silence. Complete, unbroken, decades-long silence. This is the Fermi Paradox, and it has exactly one resolution that the mathematics permits. Either we are alone, or something is stopping civilizations from being heard. Both answers, examined carefully, are bad news. Let's establish the scale of the problem before we discuss the solution. The SETI Institute, the Search for Extraterrestrial Intelligence, has been scanning the sky for radio signals since 1984. 40 years of listening, multiple antenna arrays, billions of frequencies monitored continuously. One signal of interest in 40 years. The WOW signal, detected in 1977, lasting 72 seconds, never repeated, never explained, never identified. 72 seconds in 40 years of listening. In 2020, a signal designated BLC-1 was detected from the direction of Proxima Centauri, the nearest star to our Sun. It passed initial screening. It was investigated for months. It was eventually attributed to radio frequency interference from human technology. We were so eager to find something that we briefly mistook ourselves for an answer. The silence is not a gap in the data. The silence is the data. In 1998, the economist Robin Hanson published a paper that formalized the problem. He called it the Great Filter. The argument is straightforward. For a civilization to become detectable across interstellar distances, it must pass through a series of steps: the emergence of life, the development of complex cells, multicellular organisms, intelligence, technology, the ability to expand beyond a home planet. Each step has a probability. Multiply the probabilities together and you get the expected number of detectable civilizations in the galaxy. The observed number is, as far as we can determine, 1. Possibly 0 if we are not yet detectable ourselves by the standards that would matter at interstellar range. This means that somewhere in that chain of steps there is a filter, a step or several steps where the probability is so close to 0 that almost nothing gets through. The question is not whether the filter exists. The silence proves it does. The question is where it is. There are two possibilities. The filter is behind us, or the filter is ahead of us. This is the sentence that changes the emotional weight of every space discovery made in the last 30 years. If the filter is behind us, if the improbable step was something in our past, something we already survived, then we may be genuinely rare. Perhaps the only technological civilization in the galaxy. Perhaps one of a handful. The silence makes sense, because almost nothing else made it through the same bottleneck we did. This is uncomfortable, but survivable as a concept. We are alone. We are, in some sense, the answer to Fermi's question. The silence is explained. If the filter is ahead of us, if the improbable step is something no civilization has yet survived, then the silence means something different. It means every civilization that reached our stage eventually encountered something it could not pass through. Something that stopped it completely and left no detectable trace. We are not alone in the universe. We are simply next in a line of civilizations that have not yet reached the filter. The silence is not evidence of absence. It is evidence of what the filter does to everything that reaches it. Now we have to talk about Mars. In 2021, the Perseverance rover began its systematic search for biosignatures in the Jezreel crater, an ancient lakebed that held liquid water for potentially millions of years. Conditions that, on Earth, would have been more than sufficient for microbial life to emerge and persist. As of current data, no confirmed biosignatures have been found. This is good news in one specific and important sense. In 1996, a paper in Science announced that a Martian meteorite, ALH 84001, contained structures that resembled fossilized microbial life. The claim was not confirmed. The scientific consensus eventually moved against it. But the conversation it started is still the most important one in astrobiology. If we find life on Mars, even microbial, even fossilized, even ambiguous, the implications for the Great Filter are severe. Here is why. Mars and Earth are neighboring planets. They formed from the same protoplanetary disk. They had liquid water at roughly the same time. If life emerged independently on both, in the same solar system, on adjacent planets, within the same few 100 million years, then life is not rare. Life emerges readily, given the right conditions. And if life emerges readily, the filter is not in the early steps. It is not in the chemistry of abiogenesis or the emergence of the cell. Those steps are apparently easy, which means the filter is somewhere later, in the development of complexity, in the emergence of intelligence, in the behavior of technological civilizations once they reach a certain threshold. The more common early life turns out to be, the more catastrophic the filter ahead of us becomes, because something has to explain the silence, and the easy steps can no longer carry that weight. A 2018 paper by Anders Sandberg, Eric Drexler, and Toby Ord at Oxford's Future of Humanity Institute modeled the probability distribution of the Great Filter across all possible steps. Their conclusion, under the most rigorous statistical treatment they could apply, was that the data is consistent with humanity being alone in the observable universe, and that finding even microbial life elsewhere would dramatically shift the probability toward a filter that lies ahead. The paper's final line reads, "We should not be too quick to celebrate the discovery of life beyond Earth." Let's consider what the filter ahead might look like. There are several candidates. They are not mutually exclusive. The first is self-destruction. A civilization that develops the technological capacity for interstellar communication also develops, necessarily, the technological capacity for weapons of sufficient scale to end itself. Nuclear weapons, engineered pathogens, technologies we have not yet named. The question is whether any civilization manages the transition from dangerous capability to stable coexistence with its own power. The data from our own civilization is not encouraging. We have had nuclear weapons for 80 years. We have come within minutes of using them on multiple occasions: 1983, 1995, 1962. The gap between capability and catastrophe has, several times, been measured in human error and individual judgment. The second candidate is resource exhaustion. A technological civilization consumes energy. The more advanced it becomes, the more it consumes. The transition from a planetary energy economy to a stellar one, the transition required for any civilization to become detectable across interstellar distances, may simply not be navigable. The window may be too narrow. The civilization collapses before it becomes loud enough to hear. The third candidate is something we have not thought of. This is, statistically, the most likely answer, because the filter, by definition, is something that stops everything. It is probably not something we have already identified and partially solved. It is probably something that looks, from inside a pre-filter civilization, like a normal feature of progress, something we are currently moving toward without recognizing it as a threshold. This is the candidate that produces the most consistent discomfort when examined carefully. We do not know what we do not know. And the filter is, by the nature of the problem, in the category of things that civilizations do not survive long enough to document. There is one more piece of this that is rarely discussed. If the filter is ahead, and if it has eliminated every civilization that reached our stage, then there should be evidence. Not signals, not communication, wreckage. A civilization advanced enough to build structures on stellar scales would leave marks. Dyson spheres, megastructures that capture a star's total energy output, would be detectable as infrared anomalies. Stars that simply stop emitting visible light. Signatures that do not fit natural explanations. In 2015, the star KIC 8462852, Tabby's star, was observed to dim in patterns that no natural model predicted with full confidence. Irregular, asymmetric, deep dips in brightness. The leading explanations are natural: comets, dust, stellar behavior, but none of them fully fit the data. It is almost certainly natural. Probably. But the fact that probably natural is the best we can do 400 light years away says something about the limits of what we can detect and what we might be missing at greater distances. The absence of confirmed megastructures does not mean they do not exist. It means we have not seen them. In a galaxy with 100 billion stars, we have looked carefully at a very small fraction. The silence may simply be a resolution problem, or it may be that megastructures are not built, that nothing reaches the stage where they become possible, that the filter takes everything before it gets that far. Let's return to Fermi's lunch table. Where is everybody? The honest answer in 2024 is that we do not know. We have not found them. We have been listening for decades, and the sky remains quiet. We have sent probes into interstellar space and found no signs of traffic. We have scanned billions of stars for anomalies and found one that is probably natural. The silence is consistent with two scenarios. We are the only ones, because something in the past was nearly impossible and we survived it, or we are not the only ones, but everything ahead of us has been stopped by something we have not yet identified. There is no third option that fits the mathematics. What we do know is this: the universe is old enough that a civilization which emerged 1 billion years before us, with even modest expansion, could have reached every corner of the galaxy by now. Not by traveling faster than light, just by spreading, slowly, generation by generation, the way life spreads on Earth. 1 billion years is enough time for that, even at a fraction of the speed of light. The galaxy should be full. It appears not to be. Either we are extraordinarily rare, or extraordinary things happen to civilizations that keep them from filling the galaxy. Both of these, followed carefully to their conclusion, point at us, at what we are, at where we are in the sequence, at what might be waiting further along the path we are currently on. The Fermi Paradox is not a curiosity. It is a measurement. And the measurement, read correctly, is a warning. One question: if we detected an unambiguous signal from another civilization tomorrow, confirmed, undeniable, clearly artificial, would that be good news or bad news? Think about it before you answer. Because the great filter mathematics gives a very specific answer, and most people's instinct is wrong. Drop your answer in the comments. Next video: the force that is pulling the universe apart faster than light, and what the endpoint of that process looks like for everything that currently exists. See you there.